You'll be glad to know that we're going to talk about thermal just for 1 week. It's kind of a natural consequence of the other things that we have done so far. And we've used, as you recall, Reynolds transport theorem to look at a couple of different components. And you will recall that we looked at conservation of two systems so far. The first was mass, which is just equal to density times volume. And we also looked at conservation of momentum, both linear momentum and rotational momentum. They were different in that one was a scalar property and one was a vectoral property that had both magnitude and direction. And so that made things a little bit more complicated when we used that in Reynolds transport theorem. And so what we would like to do now is we'd like to look at conservation of energy. And so energy, as we define in lowercase b, is energy per unit mass. And so energy per unit mass we can define as due to the components of internal energy plus the kinetic term, v squared over 2, plus potential energy, which is just elevation times gravity. And that's what goes into this. This is energy per unit mass. That we'll attempt to conserve anyway. And in this internal energy, hopefully this will look familiar to you, is equal to two components. It's equal to, well, we define enthalpy as the sum of the two components, which is internal energy plus pressure term, right? Pressure over density. And this is enthalpy. So, in other words, if we do the substitution, for instance, for this expression into Reynolds transport theorem, just as this component here. I'm not going to go through it because it's kind of long-winded, but we'll end up with a couple of components coming out of it. So this is basically what we've done here. This is internal energy per unit mass. And instead of the terms on the other side, which were before, you remember that this term here ultimately for conservation of momentum became sum of the forces, for instance, equals ma, which was kind of what was this. Then the terms on the right-hand side of this term become the quantities of heat flow net into the system, or rate of heat flow into the system, and rate of work done in the system, where the sign convention, which we'll talk about later, is positive with heat flow, heat energy, or thermal energy, or work energy into the system, so net in. And so we won't deal with it in this kind of Reynolds transport theorem way, but we'll look at it in two simplified forms. And the two simplified forms are the ones here and here. They're both related to each other. But let's not worry about those for the moment. Let's talk maybe in a big picture about what we're attempting to do. So what we've done so far is when we've looked at conservation of mass and conservation of momentum, we said before that those were just the corollaries of our two systems that we've dealt with in weeks 4 and 5, which was Bernoulli. And so Bernoulli, we had Bernoulli's equation, which was really a conservation of momentum equation written along a streamline. And sometimes we used conservation of mass to close that system if we had too many variables in there. When we talked about Reynolds transport theorem, we solved for each of those systems both conservation of mass and conservation of momentum, but for arbitrary volume, arbitrary control volumes. It didn't have to be a streamline, which is essentially one-dimensional. We could look at multi-dimensional flows into and out of a cube or into a curved pipe, which we did some examples for. And so in all of those systems, though, we didn't deviate from the fundamental tenets of Bernoulli, and that was it's an incompressible, well, it could be a non-incompressible fluid, but it was essentially an inviscid fluid, one which had no viscosity to it. And so by definition, if it has no viscosity, there's no energy loss in the system. And so what we want to deal with is now attempt to accommodate energy losses in the system and also look at machines which are used for the conversion of energy. And so the one useful way of us to be able to do that, I think, is to be able to think of our simple system. So let's see. Systems with energy loss. I think I can probably get away with writing it on this sheet without running out of space. And so the idea is this, that now we have a pipe which looks like this. This is our stream tube. And so this is a pipe that has fluid flowing in it. It's basically a one-dimensional stream tube, but it has a pump in it. So we have the ability to put energy into the system to be able to deal with, to be able to pump fluids, for instance. Let's choose a datum. And then let's kind of talk about what we're going to be talking about in at least visual terms, in terms of the components of Bernoulli. We know that Bernoulli has three components that we've dealt with. One is an elevation head, one is a pressure head, and one is a velocity head. And so what we could do is we could write, if we wanted to, how am I going to do this? For each of these points upstream and downstream. And let's remember that we write these things upstream and downstream by convention. Didn't matter before, but it will matter now that we do it this way. And we could look at each of those components. So this component is the elevation head at this point. This happens to be the same, doesn't have to be the same, but happens to be the elevation head at this point. Let's say we might have a fluid pressure in there that we're going to deal with. The pressure term would be equal to the pressure at point 1 divided by the unit weight. And likewise, the pressure at point 2 divided by the unit weight of the flowing fluid. It's a tube, let's ignore the pump for now, but it's a tube that has constant cross-section. So we could imagine that the velocity in this would be equal, would also be a horizontal line, right? Because it's not changing area, and continuity tells us that this would be the same. So it's V2 squared over 2G, and V1 squared over 2G. And that's what we called before. This was our energy grade line we talked about. And this was, by definition, our hydraulic grade line. Define both those terms. And for all the cases that we've dealt with, this has been, the energy grade line has been constant because there's been no way for us to be able to expend energy in the system because it's been inviscid. So inviscid just means that when I drag this across the table, I have to pull a force against it because there's some resistance on the bottom of it, which is friction. If I push it back this way, I have to push again and expend more energy against it because friction acts against motion. And so in our flow system, we have that friction. That friction really is called viscosity, or the effect is due to viscosity. And that's the mechanism by which we dissipate energy by flowing in a system. And so we can quite simply think of the other terms that we would put into a system as being a magnitude of pump head, which we'll call H sub P, which gets us up to this point, which raises, if you like, the energy in the system. And if everything was fine and our system was still inviscid, then this horizontal line would kind of be our revised energy grade line, number 2 if you like, or revised one, because we're not losing any energy in the system. In the reality, in real life, when we have viscosity, if viscosity is not 0, then we have an extra term here, which actually, if I can draw, should be doesn't need to be a straight line. Let's see if I can draw a straight line. Oh, that's not bad. So this now we'll talk about as the head loss. So this term here is equal to some head loss in the system. And so the two new concepts today are that we're able to put energy into the system by doing work in the system. A pump is one way of doing that. And also in real systems we have the influence that we can use up energy by working against viscosity. Viscosity, you can imagine if you have a very viscous fluid like syrup or maple syrup. It's Canadian Thanksgiving Day today, so let's talk about maple syrup. As you push a viscous fluid, you have to do a lot of work to be able to push it along a pipe, and therefore you're doing work against it. And so what we can think of then are our systems defined in some way. And so our system becomes just a one-dimensional system which we can draw a box for. And the box is written not so much in x, z coordinates, but more in x streamline coordinates, I would say, right, as you go along a streamline. And we would define a velocity out, which we also probably call v2. We define a velocity in, which I guess we could also call v1. We have a mass flow rate, which we've called uppercase M, which is always positive. We don't have to worry about ins and outs on the upstream and downstream side. It's just a magnitude which is through the system. And I guess that's it. And so to not jump around too much, let me just write out what we think the energy equations would look like. I guess you kind of have them there, but let me write them out just for my own edification. Yeah, so what is it? I have it written down here. So in its simplest term, I suppose, it would be, it's this expression here. It comes out of this expression here. It's basically these two. I can write them out. Why don't I write them out, because that'll force me to actually explain the terms. So Q dot net in plus W dot net in. So those are heat energy into the system, which is positive. Positive in, so it's heat. And this is positive in, which is work. Two components. And that has to equal everything on the right-hand side of that. I'm just going to write out, it's a mass flow rate multiplied through by U, which is internal energy, which is called U dot, plus V squared over 2, plus gravity times elevation, plus pressure divided by density. Pressure on the top, density on the bottom. And so if we wanted to, we can substitute this term here to define this as a function of, well, from this, right? This term up here. If you write the internal energy in terms of enthalpy and fluid pressure, then you can change this around basically to get rid of this term as a function of being able to write these two terms in terms of internal energy and pressure. And so that, if you look at this expression, is exactly this expression, right? Energy into the system due to heat, positive in, work into the system due to work that you apply as an engine. And it looks like Bernoulli, but instead of the pressure term which we used to have in here, we've replaced that pressure term with a combination of pressure and internal energy, which is enthalpy, which is this term here. So this expression is just this exact expression. Lowercase m instead of uppercase m, but that's immaterial, so you can think of it anyway. And the one thing is that we have to worry about the way that we write this. So instead of putting this as equal to at a single location, we write it upstream and downstream. So this is upstream, this is downstream. So I guess in our terminology this would be number 1 and number 2, etc., all the way through. And so we could, for a system, be able to do that. So we'll jump straight to be able to solve a system using that. So that's the first expression. So when we have to deal with enthalpy in a system, then we might like to write our, this is conservation of energy. Or if you like, it's also Bernoulli, but including energy loss. So, nothing unusual about this. We're going to use it in exactly the same way as we've used Bernoulli before, but write it in terms of, but we have these extra terms in it that allow us to deal with energy changes in the system. So that's one way to look at it. The other way to look at it as a direct consequence of this, which we won't derive, but hopefully you'll just take on trust, is this other one that looks much more like Bernoulli. And I'm going to write this out at the bottom of the page because it's the one that we'll tend to use perhaps more. It's written kind of backwards here because this is the upstream part and this is the downstream part. But if you write the Bernoulli equation as you've been used to having it, it's pressure upstream, pressure head upstream, plus elevation upstream, plus velocity head upstream, plus the pump. So in other words, if you look at this diagram here, that's kind of exactly what this is. These are units of length, so this is a pump head, so to speak, units of length also. And so this is the right-hand side of this expression here. And if you look at the downstream component, it's just equal to the same components. Pressure downstream, pressure head downstream, elevation downstream, velocity downstream, velocity head downstream, plus head loss. Everything, the same sign convention applies as before, and that is that our coordinate system is positive upwards. Okay, well, the other thing is that this right-hand term here, of course, now is this. When you think about it. And so it's no more than that. And so what it is that we've now defined Bernoulli. We have the ability to put energy into the system in terms of pump in some way, and we have the ability to have energy losses accommodated within the system, say to friction along pipes or friction in porous media, for instance, by these terms, which are merely defined in terms of length. They have to be adding apples and apples, so these have to be the same units as the other components. Our coordinate system, or our reference frame, is that z is positive upwards. Velocity is, so let's write that down, positive upwards. Velocity is positive along streamline. So it doesn't matter about, coordinate directions, etc. It's along the streamline. I guess the other important things, which I'm running out of space for, HP is positive for a pump, if you like. So if you're putting energy into the system, it's negative for a turbine, where you're using water and getting energy out of the system by taking energy out of that water. and the head loss is always positive. For exactly the reason that I mentioned about this, right? I pull it towards me, I use up energy. I reset it back to its original place, I use more energy to put it there. So the loss is always positive. And so that's Bernoulli written in terms of energy losses. So the other component that's important, so that's this expression here, which we've written out. The other one, if we're dealing with enthalpy, is written slightly differently. We've kind of combined the pressure term with the work term, and we come up with this enthalpy part, but they're basically the same expressions. And what else did I want to say that just escaped me? Oh yeah, the other way to be able to define this pump head is to be able to look at it in terms of the work. So this is the amount of shaft energy in per unit mass flow rate. So in other words, divided by gravitational acceleration. So I think this isn't the easiest way to think about it, but if you combine those two together, you end up with the pump head as being equal to the work, shaft work in, divided by mass flow rate, we've called it uppercase M, times G. So that's the other thing that's useful to remember. Pump head is equal to the work you put into the system or take out of the system divided by the mass flow rate and gravity. And hopefully if you work out the units on that, they should work out to be, well, we could check it, I suppose, right? The unit should be length. So so work is going to be in watts. So watts are joules per second, which are Newton meters per second. So that's Newton meters per second. Mass flow rate is kilograms per second. Oops. And gravity is meters per second squared. And actually, a kilogram meter per second squared, get rid of this, kilogram meter per second squared is just a Newton, what, by definition. The force needed to give a kilogram an acceleration of 1 meter per second squared is 1 Newton. So this whole term in the brackets without this is the same as this. This is a Newton. This is a Newton. And therefore the only term left is meters. And so it is actually consistent unit-wise. Okay? All right, so that's it. So those are the two equations that are useful to know. So the ones that are written here are in your sheets. Okay? Let's go ahead and use them. So we won't worry about this derivation, this derivation, this derivation, this derivation, this derivation. Okay, one thing I will add, don't go away yet, don't turn your sheet yet, is that you can also put some term on here which we call alpha, and may or may not be important. And so the assumption is that when we have, I'm getting a bit crowded here, but the assumption is if you have flow going along a stream tube, that the velocity it comes out at is uniform all the way across it. And if that's the case, alpha is equal to 1. If in reality it comes out so that it looks something different to that, then alpha is less than 1. So just a scaling factor for the fact that flow is not uniform across the stream tube. So not so particularly important. But I mention it because you have it here, right? It may be different in each of these cases. And so that's the other component to have. So Bernoulli has a pump head term. It has a head loss term due to frictional losses. But other than that, it's basically Bernoulli. Then we have to go through some gymnastics to get there, which we're not going to worry about. But you see it summarized on this yellow sheet, and we'll do some examples in a second. Okay? So why are we interested in it? Well, we're interested for a variety of reasons. You've seen these ones before, right? Again, before United changed their spots, they just changed as with their merger. I guess that's this. Exciting stuff, isn't it?
Of the many unique hazards that exist near an aircraft, perhaps there is none more dangerous than that of a jet engine.
And so one of the reasons we like to do this is because obviously jet engine is something that's not quite as simple as Bernoulli, but there's some transformation. It certainly has to satisfy conservation of mass, but we're putting chemical energy into there, and we're changing the enthalpy of the fluids that go into the system and go out of the system. And so dealing with that using standard Bernoulli, we can't manage. And so one reason to be able to look at the energy equation is to be able to deal with this.
And a picture is worth 1,000 words.
The city by the bay, again, this is San Francisco International, almost certainly. So, it's kind of interesting, it tears the truck apart, right, even before it ends up in the water. I'm not sure, I suppose they were required to remove it from the bay after the fact. So that's one form of behavior we might be interested in. So in looking at an engine, for that matter. Another one that we've kind of touched on before is the idea of pump storage. You know, it's a big thing now with, well, where's Luddington pump storage? I have no idea. Is that with renewables, for instance, with wind power and solar power, one of the big deals is that you have non-constant supply of energy. And so you have to even that out somewhere. You only get wind energy when the wind blows, and you only get sunshine during the daytime. And so energy storage is a big deal. And so there are a variety of schemes available for storage. You could use big batteries, but there's a lot of power that you're dealing with. And so one way to do it is through pumped storage. I have no idea where Luddington is. Sounds British, actually, but does anyone see where it is? Michigan. Well, that's certainly not in the UK then. Oh, Michigan. Well, didn't we just beat them? And so, but anyway, so that looks like a really. So the idea is you have a big reservoir. When energy is cheap, you pump water from low to high. Can I get back from this? If I close this, right? All of these things are showing the same thing. You have a storage location. You run the flow through it when you want to generate electricity. When you need it in times of peak demand, you know, when everyone turns their toasters on in New York City at 7 o'clock in the morning. And then when electricity is cheap in the evening, at nighttime, you do the reverse and you actually refill this reservoir from the lower reservoir and just use it as a big battery, basically, to be able to run through it. So nothing more than that. And so that's something that certainly has been around for the last 100 years. It's not particularly amazing technology. There's one of these actually in northern Pennsylvania. I was near Erie. I was surprised to find out by a group of students who did a project, a graduate design project on it. And another way of energy storage, again, which is kind of interesting, is to put compressed air underground. So same idea. You pump it underground when you can get cheap electricity. You use electricity in the turbines to pump it and compress it underground. And when you need it in times of peak demand, you just run it back through the turbines in the opposite way, and you generate electricity from it. And so instead of taking it up to an elevation and then dropping water down with its mass, you actually store the potential energy, if you like, in the elasticity, the compressibility of the gas, either in caverns, which is sometimes the case. In northern Pennsylvania, for instance, there are all these gas caverns which are in salt. You put a cased hole down, and you just circulate water around the bottom to dissolve out the salt. You retract the casing, so you get these big, long, cigar-shaped holes. They might be tens of meters in diameter and hundreds or thousands of feet, certainly hundreds of meters in height, which are cigar-shaped. They're filled with brine when you're not using them, and when you want to fill them with gas, which is another use of them, you just put natural gas in there with the same idea. When you want to use gas in New York City, when everyone turns on their toasters or ovens, I guess, stoves, to be able to, or wakes up in the morning, turns the heat on, you want to have a supply, a reservoir of natural gas, not in the Gulf of Mexico or not in Marcellus Shale, but actually close to the consumption point. And so you can do that with caverns for natural gas, but you can also do it with caverns for compressed air, but you can also do it just in aquifers. So the aquifer has a certain amount of space in the pore space, and you just fill that up with compressed air. And so those are just examples of machines, if you like, that are not very different from what we're looking at. And so we might do some examples. So that was my plan for today, was just to do, don't know why it won't get bigger. Fine. And so these are a couple, there's just a few that are in the book that, if everyone's okay with the idea of Bernoulli written in a different way, then I think that's all we're attempting to do. And so this is looking at a turbine. You have fluid going in with some velocity and with a particular enthalpy as it goes in. You have fluid coming out at a different velocity and with a different enthalpy as it comes out. And the question is, how much work do you get out of the system? So how much is this work component we get? We have a velocity in, which we know. We have a velocity, an enthalpy in that we know. We have a velocity out that we know. We have an enthalpy out that we know. And we just need to be able to use the appropriate expression to deal with it. There's no heat going into the system, so this is the expression that we dealt with before. This is the mass rate of flow. This is the enthalpy in, enthalpy out, velocity in, velocity out, elevation in, elevation out. This term is 0. This is what we want to figure out, and we just need to exchange the components. We know the enthalpy in, which is this. We know the enthalpy out, which is this. We know the velocities, both in and out, which are 30 and 60 meters a second. And the only thing that we've got to determine is the shaft work in the system. And so we can calculate that definitely as a function of this. We don't know the mass flow rates, and so what we could do is we could divide both sides through by, it's using lowercase m, we've always used uppercase m, but this is just this, which is all we're doing there. That way we don't need to be able to know what the mass flow rates are, because we can't calculate that because we don't in this case know the cross-sectional areas. If we knew the cross-sectional areas, I guess we could calculate the mass flow rates, only if we knew the densities, I guess, which we don't know. And so if we know this and this and this and this, then we get the shaft work in per unit mass. And that's all it is. And if you plug and chug with whatever the magnitudes are, you come up with some magnitude of the amount of work you get out of the system as it goes through. Nothing more than that. Okay? So it's just using Bernoulli's expression to be able to do that, where we have the terms written in terms of enthalpy rather than head losses or pump amounts, but the same idea. Okay? So we showed the example of pump storage, and so this is just an example using exactly the same. Now we don't have to worry about changes in enthalpy within the system, so if that's the case, then we can write Bernoulli's expression that neglect that. We can write it in a variety of ways. I prefer to write it, although the question doesn't do it this way. I always just remember these things in terms of heads. Upstream and downstream. Being equal to just the same amount downstream. Plus the velocity term. Plus the losses in the system. And so it's actually an interesting example because it actually shows that it's quite important to write them upstream and downstream, and how you define upstream and downstream. So upstream and downstream basically has to be written relative to the flow directions. Perhaps not surprisingly, but I guess this kind of illustrates it. So this is the flow direction, then by definition this is upstream, and this is downstream. I'm sure you're not surprised by that, but sometimes it's worth reminding ourselves that that's the case, because sometimes it's not quite obvious. And so this is just an illustration of the bag across the table issue. That for me to drag the bag towards me, I have to expend energy. For me to get it back to its initial position, I also have to expend energy. So I've expended probably double the amount of energy to take it one direction. And pumped storage schemes are the same way, is that there is no free lunch, and that there's some energy loss in the system that you never get back. And so if you want to, this question is basically looking at that. It's saying you have an upstream reservoir which flows through down to the downstream reservoir. And if you have some head losses in the system as you go through here and generate electricity, then how are those manifest? Well, it's kind of sort of self-evident, but let's go through it anyway. So you can write the expression that we have here in terms of flow if you're producing power through this. So if you're running this as a turbine, then what are these? This is written in terms of, yeah, it's written backwards. So this is the upstream part. So this is upstream pressure, upstream velocity, upstream elevation, the shaft work that's in the system. We've normally written it in terms of then the downstream pressure, the downstream velocity, the downstream elevation, plus head loss, right? So this term here is merely just on this side because it's there, right? So this, it would normally be on this side. So this is the upstream portion, this is the downstream portion. So what do we know? The big reservoir thing, so by definition, velocity A is equal to 0. Big pond assumption, VB is equal to 0. We have elevations of these which are different by, this is going to be ZA, and this is going to be ZB. And I guess, bless you, and I guess also the pressure B is atmospheric. So that's our condition. So it makes our system much simpler. So we get rid of the pressures because they're atmospheric. That's these two here. Forget I wrote this here. Let's keep this on this side here. But I was just making the point that it's there for that reason. The velocities, the big reservoir assumption, are both 0 for that reason. And the only terms that therefore exist are this elevation, the amount of work we get out of the system, and the losses we have in the system. And so if you rearrange that in terms of these, then what do we end up with? We end up with the work in, which has a negative sign on it. Elevation A is larger than B, so this is going to be positive, right? So this is the amount of energy we get out of the system. There's a loss which we subtract off that. The loss can't be more, presumably, than the amount of energy we put through it. So this loss has to be less than this positive amount. So this has to be a positive amount. And it's equal to the negative work that's in. So if this is, so this magnitude is positive. This is actually equal to the negative amount here. So this, in our sign convention, this would be positive if a pump, and it's negative if a turbine. It's not the case for us to worry about that. This is going to be positive. This can't be less than this. So this has to be positive. And so the work that we get out of the system here, just by our sign convention, is going to be equal to the elevation difference times gravity minus some amount, which is a positive amount, which in our case, for writing this expression as output, is a net output from the system. So we get energy out of the system by running the water through it. If we write it in the reverse way, which is the next way, then this has to be now the upstream, even though it seems backwards. This is now the upstream, and this is the downstream. And so if we write the expression the other way around, then these are going to be written backwards from each other. So in other words, we would have to write the expression so that it would be what? It would be, we don't have to worry about the velocities. So the only component would be, it would be the elevation of point B times G. It would be plus, let me write it the way I would like to write it. It's the elevation at B plus the pump head is equal to the elevation at A, which is now the downstream portion, plus the head loss. This is positive. And so if we just rearrange that, it's going to be equal to, now it's going to be ZA minus ZB plus head loss is equal to the pump. And so the elevation A in this particular case is equal to a number larger than this. So this is positive. This is also positive and added to that. And so the amount of power we have to put in is to get it back up. It's exactly the same amount of power to get it back up as we recovered from the machine in running it through, but there's also a loss attached to that. So to get it back up, we've got to put in the same power it took to get down. Came down, it had to change potential. We get it up with exactly the same potential, but to get it back up there, we have to expend some loss to be able to work against friction in the pipe and losses in the system. When we run it down through the system, we also have a loss that occurs, which is subtracted from the amount of energy we get from going from upstream to downstream. So both ways we run it, we get a loss. So that's all it's illustrating. And it's saying that friction acts against you, which is really what viscosity is. Friction or energy losses within the equipment act against you, so that in moving it, in moving it from here to here, you expend energy because I'm moving it with my hands. To get it back up, you expend energy. I guess it's not quite as obvious as if you're doing it against friction on a table, right? To move it towards me, you expend energy. To put it back to the same place, you expend the same amount of energy in this particular case. So, just illustrates that point. So, that's Bernoulli. And of course, well, not of course, we also did a previous question on a monitor, basically, one of these hoses with a curve in it, like used to be used for alluvial mining in the Sierras, for instance, in the 1840s, 1849s, right? The name of the 49ers is because of the gold rush, California gold rush. And so you can look at these systems also now with losses in them. And so it's no different from what we did before. What's the question? 180-degree elbow in a nozzle. Determine the loss in available energy from the section 1 to 2, and how much is lost as it goes from 2 until this velocity is at rest at velocity 3, which is 0 over here. It's in the horizontal plane, you see here, right? X and Y, and so Z is vertically upward, so it's a bend that's, well, it's a bend like this, right? Horizontal plane. So it's not like this, it's like this. And so we can just write the expression we had. And what is the expression we had? I always write it in terms of the way I think of it. Elevation 1 upstream, pressure 1 plus velocity 1 plus pump, which there is none, is equal to elevation 2 plus pressure 2 plus velocity 2 plus the loss. And so in this case it's horizontal, so this is equal, both of these are equal to 0, right? If we do that. We know the pressures. I'm not able to do the conversions in British units, but this should be atmospheric, right? So I suppose this should be 14.7 psi, is that right? And so we have this, and we have this. We have the velocities at both of these points, Actually, we don't have the velocity at this point, but we can also use the velocity. We can just use continuity, right? Velocity 2 times area 2 equals velocity 1, area 1. And or do we have velocities? No. We have one velocity and one area. So you have to calculate V2 as a function of V1, which we can do just by dividing through by area 2. So we have that. So we have velocity 1, we have velocity 2, and so as a result of that, we have the one remaining term. We can do the same. You've noted, of course, that this is upstream. This is downstream. And also, there's no pump in the system, and so there's no component there. And so this is a head loss, but if you want the loss in some other terms, then you just, I guess this is just loss times gravity, right? I think this is head times gravity. So if you multiply this whole equation by gravity, then you get this expression here. And that's the only difference. It still has to equal, right? Both sides. And if you want to know how much extra energy is lost in going from here to here, then you just write the equation along the streamline between this now being the downstream and this being the upstream. So now it would be written in terms of velocity 2 as the upstream, velocity 3 equals 0 as the downstream, and you just repeat the same thing. Presumably the elevation is also 0 as well, and just flowing onto the floor, and you're able to solve it. So that's it. So I think really all we've attempted to do is be able to define the behavior. It's written in terms of these two relatively straightforward expressions. One in terms of enthalpy, where we have enthalpy in the system and need to deal with that. Then it's written in a particular form in terms of a mass flow rate. I think we've used uppercase M for this. And also just in terms of Bernoulli, where in our sign convention, a pump is positive and a turbine. So yeah, so the things to remember: pump, positive, turbine is negative. And of course, if this number comes out to be whatever it is, if it's positive, then you're putting energy into the system as a pump. If it's negative, then you're taking energy out of the system as a turbine. This is always positive. This is always downstream. This is always upstream. And what else? And the velocity is always the streamline velocity. And if you want to be able to convert a pump into actually not a head, but into actually the power that you have to supply to a pump, which is how pumps are rated, then there's this little relationship to use here, which we've used today. And what we haven't yet talked about is the reason for us being able to be interested, or being interested in head losses, is that when you look at flow in pipes, for instance, we define pipe losses in terms of some loss factor. And the loss factor is typically written in terms of a velocity head and some non-dimensional parameter which defines it. And we'll save that for another day, actually for a couple of weeks from now to deal with. So that's what we deal with. So now we basically have Bernoulli's expression and the ability to have losses in it. So it's viscous flow, not inviscid flow, and we're able to put energy into and take energy out of the system. And that's really all we've changed.